Okay, picking up from the last video, we now want to determine if our coefficients are statistically significant. And we'll do that through the three metrics that I talked about last time. Let's begin with the t-stat. Now, because we're dealing with a sample size of 15, which is less than 30, we're going to need to use the t-tables in order to determine the appropriate critical value for t. And so let's pull the t-table over here, and we're going to be looking for a 95% confidence interval, which corresponds to 2.5% in our tails. And we have an n equal to 15, so we want to find 14 here, right? N minus 1. So it looks like we've got 2.145. So that's going to be our critical t. All right, now let's compare that 2.145 to the computed t, which is 2.68. So the intercept is statistically significant because the computed value of 2.68 is greater than the critical value of 2.145. Okay. The p-value, here we're looking for a less than 5%, and we have 1%. So it is statistically significant based on the p-value. And then in our confidence interval, our 95% interval, we look at the lower and the upper bounds, and there's no zero in here, which means that we're statistically significant. So the intercept is statistically significant. Now let's take a look at the coefficient on price. According to the t-stat, we have a computed value of negative 2.3. And whenever you see a negative t-stat, just find the absolute value, meaning make it positive, and compare it to your critical t. Well, the critical t is going to be the same, right? Because we use the t-table, we still have the same number of observations and the same confidence level, 95%. So we compare 2.3 to 2.145, and 2.3 is greater than 2.145. Therefore, we have a statistically significant coefficient on price. The p-value, less than 5%, right? It's 3%, almost 4%. But that means it's statistically significant. And then you'll notice in our upper and lower range here, we don't have a zero, right? So we end up with statistical significance from that angle as well. What about advertising? Well, if you look at the t-stat, you have 2.85. That is greater than the critical value of 2.145. Therefore, we have statistical significance. The p-value is 1%, right? So that is less than 5% statistical significance. And then you'll notice there's no zero in our 95% confidence interval here. So statistical significance. So this is a case where all the coefficients, the intercept, price, and advertising, are statistically significant. That means that we can use these coefficients from our sample to understand the larger population. We can infer because we have statistical credibility. All right, so you'll notice the pattern here. What we did with single variable regression is just being replicated here, but with more than one X variable. Let's move on. Let's talk about economic versus statistical significance. Here's a kind of a mini scenario for you. Looking at CEO compensation, it involves a lot of factors. So on the left-hand side of our equation here, we have Y, which would be CEO compensation in thousands of dollars. And then we have our beta naught, which is the intercept, plus beta 1 times A. And A is going to be the value of all assets owned by the company. And then we have beta 2 times L. That'll be number of workers in the company. And then we have beta 3 times S, which would be the percentage return on the company's stock. And then we would have beta 4 times X, which would be the CEO's experience in years. So in this case, we're correlating these independent X variables with this dependent Y variable. We're correlating these factors as explanatory of CEO compensation. And I think you would agree that most of these should have a relationship to CEO compensation. But let's see what the regression results bring. The regression results, right, we go out and we collect a sample of CEOs, and we get our Y hat. is equal to our intercept, 6,787. Now these are in thousands of dollars, which means that this is actually $6,787,000 plus 11.4 times the value of the assets owned by the company plus 14 times the number of workers in the company plus 35.1 times the percent return on the company's stock plus 79.9 times the CEO's experience in years. Okay. Notice the signage on all of these. Let's see if it makes sense. Does it make sense that they should all be positive? Does it make sense that as the assets of a company goes up, CEO pay should go up? Yeah, the bigger the company, the more the pay. Does it make sense that as the number of workers goes up, the CEO salary should go up? Yeah, because more workers, bigger the company. Percent return on a company stock. Of course, the return on the company stock is effectively a reflection of profit, and that's correlated with how much the CEO gets compensated. Sometimes CEOs are directly compensated with profit sharing plans or bonuses. And then X, their experience. The more experience they have, the more they're going to get in terms of compensation. So it does make sense, the signage on these. And that helps us understand the data, right? If you think about the data and don't get too caught up in the numbers, things will flow a little more naturally than if we just try to do the math. All right, now let's see if these are statistically significant. Well, the t-stats for all of these, A, L, S, and X, are all greater than our 1.96 that we talked about previously, because we assume we have a sample of over 30 years, so we use the 1.96. So these are highly significant. But that statistical significance doesn't mean they're economically significant. Doesn't mean that they're meaningful to us in terms of any sort of study. For example, if we look at just one of these X variables, let's take S, which is the percent return on a company stock. It says that for every 1% increase in S, we'd expect $35,000 increase in the CEO's compensation. Well, we proved that that's statistically significant, right, with a t-value of 5.25. But economically, that's almost meaningless. I mean, one, it's hard to get an increase of 1% on a stock's return. And if the CEO did that, they'd only get $35,000 more a year. And that's a lot of money, but not when you make 6.7, almost 6.8 million a year. So this relationship would statistically hold up, but it just doesn't help us much in terms of understanding the compensation of CEOs. Okay. Now, let's talk about functional form. Don't assume that all the economic relationships we deal with are linear. Now, that's kind of ironic because in our regression program, we have been assuming this. In fact, we even call it a linear regression model, which is the most common form to use. But I want you to be aware that you can use other forms, and you can do this in Excel. So let's take a look at how this works. Let's imagine that we collect data and we get this kind of relationship. Okay, so we've got commercials per week, and then we've got output per week. Maybe this is showing, more advertising, more output sold, something like that. Same thing over here. Well, let's say your data looks like this, and you then run a regression on that data using all the tools we just talked about, and the trend line is like this. Well, does that trend line look like it fits that data very well? No, because what you're doing is you're forcing a functional form that is linear, this form here, into a relationship that's nonlinear. But you don't have to do that. Even in Excel, you can choose a different functional form. If we choose a quadratic regression curve, we allow for a nonlinear relationship, mathematically something like this, you'll notice that we get this relationship. Much better fit. Okay? And you'll witness the difference in functional forms by the R-squared. If we do this particular linear relationship, we get a R-squared of 85, or 0.85, which means that 85% of the variation in sales per week is explained by commercials. But if we use the quadratic form, then we find that 99% of the variation in sales per week is explained by commercials. Well, what would you rather have? Would you rather have 85% of the variation explained or 99%? And it all comes down to using the proper functional form. Okay, so how do you do this in Excel? Well, let me show you. Let's go back to the housing data where we had a single X variable, right, square feet. and our dependent variable is home prices. And if you recall, we got this form. Notice the linear relationship that's being imposed. But if I double click on this, what it will do, I'm sorry, let me right click on it. I think that's the right one, format trend line. It'll give me these other options. I can choose exponential. I can choose linear, which is default, logarithmic, polynomial, power, moving average. Let's do the exponential. Okay. Now you'll notice that it fits it a little different. So this is the formula. The line fits a little bit different. Does it fit it better? Well, to know that, we need the R squared. And so let's go ahead and go back to format trend line. And you can actually tell Excel to put an R squared. See display R squared on chart. So I'll put that in there. Okay. And notice I get a R squared of 0.5758 with this form. Okay. If I go back to the linear form, let's see what happens to that number. So keep an eye on this 0.5758. If I go to linear, it goes up. So in this particular case, the linear form fits the data better. Okay, what about okay, so I did the exponential. Let's try the logarithmic. 0.5864 versus 0.5808 versus 0.5. So it looks like logarithmic is a better fit. Okay. All right, but you can play around with this and use whatever form gives you the best fit. The last thing I want to talk about in this section is forecasting. And forecasting is predicting the future based on the past, and it's a form of extrapolation. Example of this would be with time series data. For example, down here we have from 2009, quarter one, all the way to, it looks like our data goes from here all the way to, maybe quarter two of 2015. So we have data, we tell Excel to give us a trend line in terms of revenue. So what we're doing is we're taking the dependent variable revenue and regressing it based on the independent variable time. Okay? How does revenue change across time? Yeah. How much of the variation in revenue is explained by time? That kind of thing. We can use this data, and Nike will do this to predict future sales. Let's say we want to know what sales are going to be in quarter three of 2017. Well, we go into our program, Excel, and we create a independent variable, which would be these quarters. And when we do this, we typically use numbers for quarters. So for example, if I was going to create this, I might have quarters, and then I'd put quarter one, quarter two, quarter three, quarter four, quarter five, quarter six, that kind of thing. Let's say I'm collecting data on companies, and I'm going to collect 40 quarters worth of data. Well, I would just create just that, 40. And then I would go in and I would put my revenue here, and whatever numbers are in there, for each quarter. And then I would do the regression the same way. This would be my independent variable x. So I'd plug that in as my x variable, and this would be my dependent variable y, right? Revenue. Revenue would be explained by time. Keep that in mind, because for the project, you may be asked to do something similar. And now we want to extrapolate, right? We want to predict the future. So here we've got all these different quarters here, and we created a trend line based on our Excel regression, and we get this trend line here. So our intercept, right? And then our coefficient, and t is the proxy for time. And there's statistically significant coefficients. So this is significant, so we can use it. We can use it to predict future sales. So how do we do it? Well, we plug in for our time the quarter we're representing. So if we want to know the 35th quarter here, which would be quarter three of 2017, right? Of all our data here, that would be the 35th quarter. We would multiply that by 0.138, add it to this, and you'll get 8.97 billion. So for quarter three of 2017, we predict 8.97, almost $9 billion. Very powerful stuff. And companies do this. Companies are always projecting their future sales. They do this most notably to plan the future, but also for their investors, right? Their shareholders. Shareholders want to know how the company is going to do in the future so they can make wise investment decisions. Okay, that's it for regression analysis. We've done really the nuts and bolts and the practical tools that can be used here. There is a lot more that you can learn, but we'll save that for another class or another semester. All right, guys, if you have questions, please let me know. Thanks.